the goal for today is to be able to solve inequalities that involve absolute value and that might also involve some additional arithmetic going on inside and also outside of the absolute value. So we have to ultimately get to here. But let's begin with the slightly simpler versions that we see here at the top of this page. And I want to kind of just start by asking you to work through one of these examples by yourself. Let's actually start with equation number 3 up here on the top. So for this equation, inequality right here, the absolute value of m minus 2 is less than 8. Take 2 or 3 minutes and come up with a solution for this. And when I say a solution, what I'd like to see is both a graph of this solution on the number line and also what is the interval notation for the solution. So solve, graph, and find interval notation. So what I'd like for us to have a chance to discuss are 2 different ways that you can choose to approach a problem like this. So rather than me telling you what those 2 ways are, let me just invite anyone who would like to share their solution to share your step-by-step on this. So what did you do? Walk us through your thought process for solving this inequality. So the first approach that we're seeing to solving this inequality takes an absolute value inequality and it splits it out into 2 inequalities that don't have absolute values anymore. This is what I'm going to call strategy number 1, right? Which is to split the inequality right off the bat and make it into 2 inequalities that don't have absolute values in them. Then it's a matter of solving each of those inequalities and then figuring out how to combine those 2 solutions into a single answer. Because there's something missing here. Namely, what's missing is what's connecting these 2 inequalities. When we first started talking about the topic that we're currently on, we spent quite a bit of time wrestling with, well, how do we solve 2 inequalities at the same time and combine their answers into a single answer? And back then, the theme was that we would combine them together using either a logical word and or using a logical word or. So if we're going to do it this way, we need to decide which of those 2 methods of combination that we want for this combination of inequalities. That's the first question that I have when it comes to how to make this method work. The second question that I have is, how come m minus 2 changed into m plus 2 in this rendition of the solution? On the one hand, this approach to the solution takes the m minus 2 and trades it out for an m plus 2, and it leaves the other side intact. Your suggestion is, why don't we, instead of switching something on the left side of this inequality, why don't we switch something on the right side of this inequality? So instead of m plus 2 is less than 8, in your method, you're saying, well, let's leave this plus as a minus, but change this 8 into a negative 8. That would change our method of solution here, because then I'd be adding 2 to both sides. I would get negative 6 instead of positive 6 for that portion of the inequality, and that means that my diagram here would move over into something that looks more like this. So I'd be shading to the left of negative 6, and then the interval notation for that bit would be negative infinity to negative 6. So that choice seems also to change the solution that we get.
I just have a question.
I would say that this solution is a little closer to where we want to be, but it's still missing a couple of things. It's missing this logical connective. It's missing the and or the or that tells us how to merge these 2 things together. And there's also one other bit that I don't yet quite agree with. Did anybody else that used this approach to split the inequality into 2 get something that was still different than what we have up here? So in your approach, instead of putting the negative sign on the right side of the inequality for this version, you put it on the left side. So let's look at what happens when we do that. Blot this out over here. So we have less than 8, but then we put a negative out here. And now let's be really careful, right? If I put a negative out in the front of this quantity, what I'm really doing is I'm taking the opposite of the entire quantity. So what I really need here is parentheses. Negative the quantity, m minus 2. And that's going to change our game a little bit, because now we have to do a little bit more work to solve for that m. Let's actually do that work and see what changes. So how would I get the m by itself? in the inequality over here? What might be the first step that I would try?
Distribute by the -1.
That sounds like a good plan, right? In our general strategy for solving an equation or an inequality, our first move is typically to try to simplify both sides, which involves here distributing the multiple -1 across the subtraction on the inside. So what that gives us then is minus m plus 2 is less than 8. Okay, then what? Now that I'm simplified on the left-hand side, what do you want to do next?
I
Subtracted 2 from both sides. So if I do that, then on the right side of the equation, I get my 6 again. It's a familiar 6. But on the left side of the equation, I end up with minus m is less than 6. So I have one more step to do that we didn't have to do before. How do I get this m by itself? Divide by -1. Okay, so I divide by -1 on both sides. I end up with a -6 again on the on the right-hand side. -6. I end up with an m on the left-hand side, and here we go. But wait a minute, isn't that the same thing that I have over here?
You gotta flip it because of the -1.
Yes, that's the thing that changes, right? In this very last step, I divided both sides of an inequality by a negative number. And that's the one time that we know, multiplying and dividing by a negative number on both sides of an inequality, that's the one thing that we know of that switches the sense of an inequality. So in that last step, this less than needs to turn into a greater than. And so this method, too, changes the picture of what our solution is ultimately going to look like. So it changes it in that -6 is still the endpoint of this interval, but now we're shading not to the left, but to the right. And so my new interval for that piece is -6, comma, infinity. And it turns out that if we're going to use this method of splitting apart the inequality first to solve an inequality with an absolute value, this is the correct way to do it, right? Which is to, anytime an absolute value goes away, this is true whether we're talking about equations or whether we're talking about inequalities. Anytime an absolute value goes away, it leaves us with two versions of itself. The positive version of itself, in other words, the version with the same sign, m minus 2. But it also leaves us with the opposite version of itself, minus the quantity m minus 2. And so if you're looking for a takeaway from this method, which is true whether we're solving equations or whether we're solving inequalities, that anytime I have absolute value of something, I'm just going to put a smiley face here because it doesn't matter what's on the inside, and whether I have an equal sign or whether I have a less than sign or a greater than sign or whatever, and then I have something on the right-hand side. Let's just make it a star. So this is kind of a symbolic diagram of what's happening here, right? That an absolute value, when it goes away, always leaves us with both the original quantity itself, but then also the opposite of that same quantity. But that the rest of the equation or the inequality remains the same. Equals star, or less than star, or greater than star, or whatever. So the inequality or the equation remains the same, but we end up with two versions of it, one in which the left-hand side, the stuff that was inside the absolute value, has been reversed, and the other in which it's been preserved. And so that's why when we got rid of the absolute value around the m minus 2, we got one inequality where we just had m minus 2, and the other one where we had minus the quantity m minus 2. And in the process of solving each one of those, we end up sort of defining what each of those pieces tells us about this absolute value inequality. But we're still missing the logical connective, because we still don't have a single answer to this inequality. We have two different intervals. And so the question is now, how do we combine those two intervals into a single answer? Do we want an and for our compound inequality, or do we want an or for our compound inequality? What do you think? Oops. And, or?
Would it be and since they overlap?
Ah, okay. So if we're thinking ahead to what our ultimate answer is probably going to look like, our ultimate answer is probably going to be just a chunk, a finite chunk, with both a left-hand endpoint and a right-hand endpoint of the number line, which would suggest to us that we probably want the and to look for the places where these two intervals overlap. And it turns out that that is the case for this inequality. So I think the drawback of using this method 1 that we're talking about for solving absolute value inequality, the drawback is we have to consider this and or question separately. Right? And anytime our original absolute value inequality uses a less than symbol, we end up with a conjunctive, an and compound of our two inequalities that it leaves behind. Let's chase down the result of that first before we go back and talk about when an or might be appropriate. If I take this green interval and this purple interval and I and them together, in other words, I find the set theoretic intersection of those two, I look for just the overlaps, what interval do I end up getting? If I look for the overlap between the green and the purple, where is it going to live? How far to the left do these intervals overlap? Just to -6. Right? It doesn't go any further to the left than -6 because once we cross -6, we no longer have the purple interval. So it goes as far to the left as -6, and for the same reason it goes as far to the right as 10. And we shade everything in between because that is where these two intervals overlap. So the graph for my answer is going to be this orange segment of the number line. That's where the green and the purple overlap with one another. And what would be an interval notation for that line, or for that segment rather? From left endpoint to the right endpoint? Just -6 and 10. And then what notation would I use to indicate whether or not the -6 or the 10 are included or excluded? What do I need here? Parentheses, because?
It doesn't include.
Because this interval doesn't include its endpoints. Great. So that then would be a solution for this absolute value inequality. And it was important for us to choose and here instead of or, because what would have happened if I had chosen or instead of and? How would my answer have been different? What happens if I or these two intervals together instead of and? What am I looking at? Say again? Right, so for an or, I want to include not just the overlaps, but I want to include everything that either of those intervals covers. And so how much of the number line do I end up covering if I'm asking for what is covered by either green or purple or possibly both? I end up covering the entire real number line. If I were to or these two things together, everywhere on the real number line is either a part of the green set, the purple set, or both. And so if I choose or instead of and, my answer at least is very different than if I had chosen and in this case. So if you choose to use this method of solving an absolute value inequality, then not only do you need to navigate this splitting apart, right, of something absolute value going away and it leaves behind both itself and its alter ego over here. But you also need to choose the right method of compounding the two inequalities together. And which method you choose actually depends on whether your original inequality is less than or whether your original inequality is greater than. And so then the rule of thumb there is that if I start with an absolute value inequality, which is absolute value of something is less than, then this becomes an and when it splits apart. Whereas if we start with an absolute value inequality that's greater than, that becomes an or if we split it into a compound inequality. So it creates, this method of solution is kind of nice, but it creates this extra overhead of having to remember not only how to split apart the absolute value, but also how to compound the two inequalities that you get when you split them apart. So this is a method that I typically teach in this course. But I don't want this to be the end of the story because there's one more method that I'd like for us to get some practice with that's a little bit less, it's a little bit more foolproof, maybe is a way to put that. It takes away some of our ability to make the wrong choice in this whole process, and that's always nice.